Before AI could learn from basically the entire internet, it had to start somewhere much, much simpler. It had to follow the rules. So today, we're going to go back in time to meet the brilliant, rule-based ancestors of the AI we use now. The systems that first tried to capture human genius, one if-then statement at a time. So, I want you to imagine the challenge back in the early days of computing. What if, and this was a huge what if, you could somehow capture all the knowledge and the entire decision-making process of, say, a world-class doctor or a master chemist and put it inside a machine? That really ambitious goal is what sparked one of the first major breakthroughs in artificial intelligence.
And the first real answer to that question was something called the expert system. Now, this was an AI that could learn like we think of it today. It couldn't just improvise. No, this was a system that was painstakingly programmed to copy a human expert's logic. It was an attempt to digitize a brilliant mind, one simple if-then rule after another.
So how do they actually do it? How do you get a machine to think like an expert? It wasn't magic, of course. It was all about a really clever, really organized structure. Let's peel back the layers and take a look inside. Okay, so an expert system has a few main parts, and each one has a really specific job. You've got the knowledge base, which is kind of like the system's brain or its memory. Then there's the inference engine. That's the thinker, the part that's actually solving problems. And then you've got the pieces that talk to the user and explain its own reasoning. But we're going to focus on those first two, because that's where the real magic happens.
The knowledge base is really the foundation of the whole thing. The best way to think about it is like a massive digital library that holds two things: facts and rules. A fact is super simple. A fever is a body temperature over 100.4 degrees Fahrenheit. A rule is what connects those facts. If a patient has a fever and a sore throat, then you should consider the flu. This is literally where all the human expertise lives.
So if the knowledge base is the library, the inference engine is the master librarian. It's the active thinker in the system. It takes a problem, like a list of symptoms from a person, and it just systematically searches that library of rules, applying them one by one until it reaches a logical conclusion.
And this thinking can actually happen in two main ways. The first is called forward chaining. It's kind of like a detective gathering clues: fever, headache, cough, and then following that trail of evidence to find a suspect, or in this case, a diagnosis. The other way is backward chaining, which is more like a lawyer who starts with a hypothesis: I think this patient has the flu, and then works backward to find evidence in the symptoms to prove it.
Let's see this in action with a really simple flu diagnosis. A user enters the facts. I have a fever, a headache, and a runny nose. The inference engine scans its rules and bam, it finds a match. It fires that rule, which then generates a brand new conclusion: possible flu. It's simple, it's logical, and back then, it was absolutely revolutionary.
And look, this wasn't just some academic theory. These systems had a huge real-world impact. Mycin was in hospitals diagnosing blood infections. Dendrel was predicting chemical structures, sometimes better than human chemists. XCon saved a major corporation millions. Hearsay was even used by the military for sonar detection. This was serious, powerful technology. So just how valuable were they? Well, that XCon system we just mentioned, get this. It saved its company, DEC, an estimated $25 million a year. And this was back in the 1980s. That's a staggering amount of money, and it just proves that this was truly an industry-changing technology.
Expert systems were amazing at using knowledge, but that raised a totally new problem. How do you organize all that knowledge in the first place, right? How do you create a universal structure for it so that different computer systems can share it and build on it? Well, what you need is a blueprint.
And that blueprint is called an ontology. Now, it sounds super complicated, I know, but the core idea is pretty straightforward. It's a formal set of rules for defining concepts and, this is the most important part, the relationships between those concepts. It's a way to give data meaning, so a machine doesn't just see a bunch of words, it sees a structured model of the world.
Think of it like a library's catalog system. A catalog doesn't just give you a big list of books. It organizes them by category and shows how they relate to each other. That's what makes it easy to find things. An ontology does the exact same thing, but for digital knowledge. Or think about a family tree. It defines concepts like parent and child, and relationships like is parent of. By understanding that structure, a computer can start to infer new facts that aren't even explicitly written down. Like, if it knows Anna is John's sister, it can reason that they must share the same parents. That ability to infer new information is incredibly powerful.
So, with these brilliant expert systems and these organized ontologies, it really seemed like AI had it figured out. But this whole approach, it wasn't the final answer. The pioneers were about to hit a wall, a big one, that revealed the fundamental limits of trying to build a mind entirely out of rules.
So here were the big problems. First, these systems were brittle. If they ran into a situation that wasn't covered by a specific rule, they just broke. They were also static. They could never learn from new data or get better on their own. They were incredibly high maintenance, since every single rule had to be programmed by a human. And probably the biggest issue, they just couldn't handle the messy, unstructured data of the real world, things like images or natural language.
But those limitations weren't a dead end, not at all. In fact, they were the exact catalyst needed for the next great leap in AI. The challenge of overcoming these brittle, static systems is what led directly to the flexible, learning AI that we're all so familiar with today.
And that leap brought us to the techniques that define this modern era. We're talking machine learning, deep learning, NLP. These systems completely flip the script. Instead of being fed rules by humans, they're designed to do the one thing expert systems could never, ever do: learn. They find the patterns themselves by analyzing just massive amounts of data, whether it's text, speech, or images.
I think this quote just captures the shift perfectly. Early AI was like a brilliant student who had memorized every single textbook, but couldn't learn anything new on their own. Modern AI, it's like a student who can read the entire internet and actually learn from it. One was a genius with a perfect but totally finite memory. The other is a perpetual student, capable of understanding a nearly infinite stream of information.
So, that brings us to today. We went from an AI that just followed rules to one that learns from data. And it leaves us with a really fascinating question. What's next? If the first era was all about logic and the second was all about learning, what's going to define the third? Thanks for watching.
How did early attempts in artificial intelligence try to mimic human expertise and understanding? Long before large language models and neural networks became, well, household names.
That's a great question to kick us off.
Today, we're taking a deep dive into two really foundational concepts in AI: expert systems and ontologies.
Yeah, we'll unpack what these actually are, how they work, some of the fascinating real-world problems they tackled.
And crucially, why AI eventually kind of moved beyond them.
Exactly. There were limitations.
So our mission for this deep dive is simple: give you a clear, structured understanding of these early AI breakthroughs.
Think of it as a shortcut, maybe, to appreciating the absolute roots of artificial intelligence.
And how the whole idea evolved of how we get machines to think or reason in the first place.
Yeah. Get ready for some, hopefully, aha moments as we explore how computers were first taught to become experts in really specific areas.
Okay, so when we talk about early AI trying to mimic human expertise, what was the very first major attempt that came out of that whole ambition? How did it fundamentally try to capture human knowledge?
That would definitely be the expert system. At its heart, an expert system is a computer program.
Right.
And it's designed to simulate the decision-making ability of a human expert. But, and this is key, in a very specific domain.
Like medicine. Right?
Medicine, engineering, finance, chemistry.
Yeah.
Very focused fields. Now, it doesn't think like a human, not in the conscious sense we understand.
Okay.
But it follows these strict if-then rules to reach conclusions. And all those rules are based on expert knowledge that's been carefully put into its system.
So if it doesn't think, but just follows if-then rules, isn't that just, a fancy flowchart? What made it intelligent enough to be called an expert system, not just, say, an automated process?
That's an excellent point. It really gets to the core of it.
Yeah.
What set expert systems apart was their ability to reason with knowledge, not just raw data.
Knowledge, okay.
Yeah. And speaking of knowledge, the source material makes this really important distinction, doesn't it? Between data, information, and actual knowledge.
It does.
For listeners maybe thinking data is data, could you maybe explain how a system might literally break down or maybe give terrible advice if it confuses these or if it doesn't have true knowledge?
Absolutely. It's this fundamental hierarchy that was just crucial to early AI.
Right.
So data is just your raw facts. Think of the number 98.6. That's data.
Okay, just a number.
Information is when you organize it, give it context. So temperature equals 98.6 degrees Fahrenheit. Now it has meaning.
Got it. Contextualized.
But knowledge, that's when you have these meaningful insights derived from that organized data. Like
Right.
knowing 98.6 degrees Fahrenheit is a normal body temperature.
Ah, the interpretation.
Exactly. Expert systems were built on this hierarchy. Without understanding these differences, the system literally wouldn't know how to interpret information or make meaningful conclusions.
It can lead to completely wrong, maybe even dangerous advice.
Totally incorrect, nonsensical stuff. Yeah, it really is the foundation.
Okay, that makes it much clearer. It's about the meaning, the insight, not just the numbers.
Right.
So if we're trying to, as you said, bottle a human expert's brain into a machine, what are the actual core components? What makes up an expert system? Let's maybe start with the central brain and the reasoning parts.
Yeah. Good place to start. You've really hit on the essence there. The first, and probably the most important part, is the knowledge base.
The memory.
Exactly. Think of it as the system's brain's memory. It's this big repository of facts and rules that have been painstakingly, really carefully collected from human domain experts.
Okay.
And we talk about two types of knowledge here. There's declarative knowledge. Those are just facts. Like fever is a body temp over 100.4 degrees Fahrenheit. Simple fact.
Okay.
And then there's procedural knowledge. These are the rules, the if-thens. Like if fever and sore throat, then possible flu.
Logic.
Yeah. So in a medical expert system, for instance, the knowledge base would hold all the known disease symptoms, treatment guidelines, diagnostic rules, everything the human expert knows.
Right. So if the knowledge base is the memory, what's the active thinking part, the reasoning engine?
That would be the inference engine. This is the brain's reasoning mechanism.
Okay.
It's the logical processing unit that actually applies reasoning to the facts and rules stored in that knowledge base to derive conclusions. It uses that classic if-then logic.
Then how does it do that? Are there different ways?
Yep, two main ways typically. First is forward chaining. This is data-driven reasoning.
Data-driven, meaning?
Meaning it starts with the known facts, the input data you give it, and it applies the rules it knows to infer new facts, and it keeps going until it reaches some goal or conclusion.
So, okay, if a patient comes in with certain symptoms, it's like the system sifts through its rules using those symptoms to arrive at a diagnosis, like diagnosing the flu.
Exactly. Perfect example. If the system gets facts like patient has fever, patient has headache, patient has runny nose,
Right.
and it has a rule in its knowledge base that says if fever and headache and runny nose, then possible flu.
Then the forward chaining engine just fires that rule.
Precisely. It concludes the patient might have flu. It's driven entirely by the incoming data, the symptoms.
Okay, that makes sense. And the other type of reasoning, you said there were two. Is that like working backward from a potential answer?
You got it. That's backward chaining. This one is goal-driven.
Goal-driven, okay.
So here, you start with a potential goal or hypothesis. Let's say, does the patient have flu?
Right.
The system then actively looks for rules in its knowledge base that support that goal. And importantly, it might ask questions to verify the conditions needed for those rules.
Ah, so it's trying to confirm or deny the hypothesis. It works backward from possible flu and asks, okay, does the patient have a fever? Does the patient have a headache?
Exactly that. It essentially asks, what do I need to know to confirm this specific goal?
Got it. Okay, so that's the core processing. Knowledge base for memory, inference engine for reasoning, using forward or backward chaining. But what about the other vital parts? The bits that let it interact with us or keep track of info during a session. How do we actually talk to it or, crucially, understand why it made a recommendation?
Yeah, those are critical too. That's where the next set of components comes in. First, obviously, the user interface.
The front end.
Right. The communication bridge. Could be a simple chatbot, maybe a web form. It's where users input their information and where they receive the decisions or suggestions back.
Like that WebMD symptom checker example.
Exactly like that. You click check boxes for your symptoms, that's the input, and it gives you likely diagnoses, that's the output. Simple UI.
Okay, but what if the system makes a recommendation, say a diagnosis, and I want to know why? I mean, how do you build trust in an AI if it's just, spitting out answers without explanation?
That is a huge point, and it was addressed by the explanation facility.
Explanation facility.
Yeah, think of it like the system's teacher. Its job is to explain how and why a specific conclusion was reached.
Ah, traceability.
Exactly. Yeah. It's absolutely crucial for building user trust and making the system transparent, not just a black box.
So in like a legal expert system.
It would show you exactly which laws, which case precedents, which specific facts from the input supported a particular legal recommendation. Opens it up.
That's really important. Okay, and getting the knowledge in there in the first place. Or updating it. I mean, human expertise changes, right?
Yeah.
New discoveries happen. That sounds like a constant job.
It was, and it's a major challenge we'll come back to. That input and update process is handled by the knowledge acquisition module, sometimes called the developer interface.
The backstage controls.
Pretty much. It's the tool that helps the domain experts, the doctors, the engineers, collaborate with the AI engineers to input new facts, update rules, refine the knowledge base.
So that's where the human expert plugs in.
That's the essential human-in-the-loop part for building and maintaining it. Imagine doctors working with developers to add, say, new COVID-19 rules into a medical system back when that emerged. That's the module they'd use.
Okay. And what else? You mentioned tracking info during a session?
Right. That's the working memory, sometimes called the fact base. It's just temporary storage.
Like RAM.
Sort of, yeah. It holds the current facts relevant just for the reasoning session that's happening right now. So when you're diagnosing that patient, it temporarily stores fever, headache, nausea for that specific interaction. It gets cleared for the next one.
Makes sense. Keeps things organized per session.
And finally, some systems had external interfaces. These are optional links.
To what?
To external databases or other software. This lets the expert system maybe fetch live, real-time data, think stock prices for a financial advisor system, or send its results out to another program.
So it could interact with the wider world data-wise.
If needed, yeah, adds another layer of capability.
Wow, that's quite a sophisticated setup for early AI.
Right.
It's incredible to think these systems were having real, tangible impacts decades ago.
Right. Here's where it gets really interesting.
Of all those real-world applications you mentioned, Mycene, Dendrol, XCon, Hearsay, which one do you find the most, surprisingly effective looking back? Yeah. And why?
Oh, that is a tough choice. They were all pretty groundbreaking in their own domains.
Yeah.
I mean, MYCIN in healthcare, diagnosing blood infections and suggesting treatments. That's serious stuff back in the 70s.
Basically WebMD, but with actual diagnostic capability almost.
Kind of.
Yeah.
And then Dendrol in chemistry, predicting molecular structures from spectral data. It's a hugely complex scientific task.
Absolutely.
But maybe just for sheer business impact, XCon for DEC, automating computer system configuration, saving them $25 million annually.
Wow.
That's a massive measurable impact on a company's bottom line. That one always stands out to me.
Yeah, hard cash savings are hard to argue with. And Hearsay for voice recognition, even in a noisy environment like submarine sonar. That's impressive too.
It really shows the breadth, doesn't it? From medicine to manufacturing to military.
Definitely a testament to that early AI ingenuity. But if they were so impactful, hitting these different areas, it raises that important question you hinted at earlier.
To limitations.
Exactly. What were the inherent challenges? Why didn't they just take over everything? What stops them from scaling broadly and ultimately led AI researchers down other paths? It feels like they had so much promise.
They absolutely did have promise, but they also ran into some really significant fundamental walls.
Such as?
Oh, remember how we said the knowledge base was built from manual rules? Painstakingly created by human experts?
Yeah, the knowledge acquisition part.
That made it incredibly hard and expensive to keep them up to date. Domains evolve, science changes, new information comes out.
And every single change meant manually rewriting rules. A huge bottleneck.
A monumental task, yeah.
Okay.
And crucially,
They couldn't learn.
bingo, they could not learn from data. There was zero improvement over time unless a human programmer explicitly went in and made changes. They were static snapshots of expertise.
So brittle then. What if the rules were wrong or incomplete?
Exactly. If you had incomplete rules, or worse, conflicting rules, the system could easily break, just stop working, or give totally incorrect results. Very brittle.
Right.
And maybe the biggest one, they just weren't scalable to really complex, messy, real-world problems. Things like computer vision, understanding natural human language, natural speech.
Things that aren't easily boiled down to simple if-then rules.
Precisely. Those domains are inherently ambiguous, they're vast, they're constantly changing in subtle ways. Rule-based systems just couldn't cope with that level of complexity and nuance.
Okay, so expert systems were brilliant for very specific, well-defined knowledge, but struggled with ambiguity, learning, and scale.
That's a good summary.
So if that approach hit a wall, where did researchers turn next to try and give machines a better grasp, not just of rules, but of knowledge itself, its structure, its meaning?
Well, that brings us very nicely to our second core concept for today, ontologies.
Ontologies, okay. What exactly is an ontology in the AI context? It sounds a bit philosophical.
It has roots there, but in AI, it's more practical. An ontology is basically a structured way to represent knowledge.
Structured how?
It defines the concepts, the things in a domain, their properties or features, and crucially, the relationships between those concepts.
Yeah.
And the key is it's done in a formal way that computers can understand and, importantly, reason with.
Formal, explicit, shared conceptualization, right? Those are the key words often used.
Exactly. Formal means it follows specific structural rules. Explicit means everything's clearly defined. Shared means it's agreed upon by a community or system. And conceptualization just means it reflects a particular view of some part of the world.
Right. But that still sounds a bit abstract. What's fascinating, I think, is how relatable these ideas can become with a few simple analogies.
Yeah, analogies help a lot here. What's a good one?
Well, think about a library catalog, like the old Dewey Decimal System, or maybe Library of Congress classification.
Okay, I can picture that.
Books are classified into categories, right? Science, history, fiction. Each book gets a code linking it to a subject. Some books might even be related across categories, like history of science, could link to both history and science.
Yeah.
That whole structured classification system, that is an ontology in action. It organizes the knowledge of the books based on defined relationships, making it easy to search, browse, and find related items.
That's a fantastic example. Instantly clicks. It organizes knowledge, makes it discoverable through relationships. What about another one? Something simpler, maybe.
How about a family tree?
Okay.
In a family tree, you have classes of things. Parent, child, sibling.
Right.
You have specific instances. John is an instance of the class person. Anna is also an instance of person.
Got it.
And then you have relationships connecting them. Anna has sibling John, or Mary is parent of John.
Okay, simple relationships.
This whole structure, classes, instances, relationships, is a simple ontology of family connections. And what's powerful is you can infer new facts from it.
Like what?
Like you can infer that John's mother is also Anna's mother, even if that specific link, Mary is parent of Anna, isn't explicitly drawn in the tree. The structure itself lets you reason about the relationships.
Ah, I see. So the structure implies connections. The ontology gives the machine a kind of map of meaning, not just a list of isolated facts or rules.
Exactly. It defines the landscape of knowledge for a domain.
So why are these structured knowledge representations, these ontologies, so useful in AI? What's the core benefit they bring?
Well, they're crucial for several reasons. First, as you said, they give meaning to data. Machines don't just see isolated words or numbers, they see how concepts relate, they see structure. This allows for much deeper comprehension.
Okay, deeper understanding.
Second, that structure helps in reasoning. It allows systems to infer new facts from existing ones, like the family tree example. The relationships enable logical deduction.
Right, inferring new knowledge.
And third, maybe most importantly for practical applications, they make data shareable and understandable across different systems. This idea is called semantic interoperability.
Semantic interoperability, meaning different systems can talk the same language.
Precisely. Imagine trying to integrate databases from, say, sales and manufacturing. If they use different terms for the same thing, it's chaos. An ontology provides that common, agreed-upon vocabulary and structure so the systems can understand each other's data.
Okay, so they make data smarter, more connected, enabling integration and reasoning. Sounds pretty powerful. But I imagine, like expert systems, they also had their own set of challenges. What limited their widespread universal adoption?
Oh, absolutely. They aren't a silver bullet either. Building and crucially maintaining ontologies requires a lot of effort. You need domain experts to sit down and meticulously define all the concepts and relationships. It's time-consuming.
So another knowledge bottleneck, in a way.
A different kind, yes. And they work best for domains where the knowledge is relatively well-structured and stable. Think anatomy or maybe an academic curriculum. The concepts and relationships don't change that rapidly.
Okay, so not great for fast-moving fields.
Or for unstructured data. They aren't very suitable for making sense of messy, unstructured stuff like raw text from the internet, images, audio, where context and meaning are fluid and complex.
Right, the kind of data that dominates the modern world.
Exactly. And they also have limitations in capturing uncertainty or probabilistic relationships. Some are probably a sibling. Ontologies are typically more about definite, crisp relationships. Real-world decisions often involve likelihoods, not certainties.
Okay, so good for structure, less so for ambiguity, unstructured data, and probabilities.
That's a fair summary.
So we've seen how expert systems tried to bottle human expertise with these if-then rules, and ontologies tried to map out knowledge with concepts and relationships. Both powerful ideas, but both hitting these inherent limitations we've discussed.
Yeah.
So what does this all mean in the grand scheme of AI development? Why did the AI world, for the most part, eventually move beyond these powerful yet clearly constrained approaches? What was the big shift?
It really boils down to synthesizing those limitations we talked about. They became sort of insurmountable hurdles as AI research ambitions grew.
Right.
Rule-based systems, the expert systems, they were just too limited in flexibility and scalability. You couldn't easily adapt them to new situations or make them handle truly large, complex problems without needing an army of human knowledge engineers constantly tweaking the rules.
The brittleness and maintenance nightmare.
Exactly. And ontologies, while really elegant for structuring knowledge, still required that intensive manual creation and upkeep. They didn't automatically adapt to changing data or evolving domains without significant human intervention.
And the big missing piece for both.
The learning capability. Neither approach could fundamentally learn or improve from experience or new data on their own. They were programmed, not trained.
Right. Static knowledge.
Static knowledge. And crucially, as we touched on, both struggled profoundly with the messy reality of the world. Unstructured, ambiguous, noisy data. The kind of data pouring in from sensors, images, social media, natural language.
Which is exactly what modern AI thrives on.
Precisely. These limitations, taken together, really paved the way for the modern AI techniques based on machine learning and neural networks that have largely taken over the field since then.
Okay, so let's recap briefly. We've explored these foundational ideas. Expert systems, trying to bottle expertise with rules.
And ontologies trying to map knowledge with structured relationships.
Showing how early AI really grappled with making human knowledge actionable for machines. Hopefully, you listening now have a deeper appreciation for these building blocks of AI, and importantly, how and why the field evolved.
Yeah, these early systems, even with their limitations, laid absolutely crucial groundwork. They proved the power and the challenge of codifying human reasoning and representing knowledge formally.
Definitely groundwork worth understanding.
And maybe here's a final provocative thought for you to consider as you reflect on this deep dive. Even now, as modern AI, machine learning, excels at learning patterns from these vast unstructured data sets, what might be the lasting value of that older idea of explicit, interpretable knowledge representation?
Are they completely obsolete?
Well, could there be a future, perhaps, where the strengths of both approaches the clarity and explainability of rule-based systems or ontologies, and the adaptive learning power of machine learning are truly integrated?
A hybrid approach.
Maybe. What aspects of human intelligence or complex decision-making might still benefit most from being codified in those clear, explainable ways we saw in expert systems and ontologies, even alongside powerful learning systems? Something to think about.